Hello students, I'm Anubhav Nath, and today is the section second of the chapter S block elements. So in this chapter, we will discuss about the alkaline earth metals. That is the section second of session. So in this chapter, we will finish about talking about these S block elements. So we shall start. So firstly, I have told you about the alkaline earth metals in the last session, like what are the alkaline earth metals or why they are called as alkaline earth metals. Because their hydroxides are alkaline in nature, that's why they are called alkaline earth metals. And their oxides and hydroxides are found in nature in the earth's crust. Crust means the upper layer of the earth's surface. That's why they are called the alkaline earth metals. So what are these metals? These metals are beryllium, magnesium, calcium. Let me just pull out the pointer here. Okay. So beryllium, magnesium, calcium, strontium, and barium. So these five are mainly called the alkaline earth elements or alkaline earth metals. There is another element here, that is radium. But since it is radioactive in nature, because you have all known about radium is an radioactive element. That's why it is not written here, but radium is also an alkaline earth metal. So all these alkaline earth metals have the common electronic configuration, which is noble gas, and then it is followed by NH2. So there are 2 electrons in the s orbital in the valence shell of the alkaline earth elements. So what is the valence shell? The last shell that is actually sitting there in an atom or element. So that is called the valence shell. And if the valence shell is s, so s orbital can hold up 2 electrons at max. So the electronic configuration of all the alkaline metals will be the last valence shell, that is s orbital, that will be fulfilled by 2 electrons, and it will be followed by a noble gas configuration. So an alkaline earth metal will always try to pull off the 2 valential electron, because if it does so, it will have the electronic configuration of a noble gas. And you all know, like, the noble gas are actually very much stable in nature. Their electronic configurations are very much stable in nature. That's why alkaline earth metals are readily available to lose its outermost electron to the atmosphere and go to the dicationic species. That's why you will find every alkaline earth metal in the oxidation state +2, like beryllium +2, magnesium +2, and so on. So these alkaline earth metals will be found as their +2 salts, like beryllium sulfate or beryllium chloride or calcium sulfate or calcium chloride. So these kinds of compounds are actually known in nature because their corresponding alkaline earth metal +2 compounds are very, very stable, because all these possess this noble gas configuration. Now, one by one, we will go through this atomic or ion. So different parameters we will discuss about. Okay. So firstly, we will discuss about the atomic or the ionic radii. Then we will go to the ionization enthalpy, then hydrogen enthalpy, and so on. So firstly, we will start with the atomic and the ionic radii. Now, you all know, like from beryllium to barium, it is actually going from the top to bottom in the periodic table. And in a periodic table, in a specific group, you know, like when we go from top to bottom, the principal quantum number, that is the n, that is noted here. You can see here it's n, that is the principal quantum number. That is the valence shell electronic configuration of the valence shell. So this actually increases. That's why the size of the elements also increase. So in a group, in a periodic table, from top to bottom, the size increases. So the atomic or the ionic radii also increases. That's why it is written like from beryllium to barium, the size is actually increasing from top to bottom. But here another point is noted, that is the S block elements, that is the alkaline earth metals, have their atomic or ionic radii smaller than those of the alkali metals. So what are the alkali metals? You have known about, you have gone through the last session, like I have told about these alkali metals. They have the electronic configuration noble gas followed by NS1. And these alkaline earth metals have the configuration noble gas followed by NH2. Now, because of the increased nuclear charge, now because you have gone through the periodic table a little bit, so I can tell you this phenomena. Like from the alkali metal, it is in the extreme left in the periodic level. Here, if you consider this as a periodic table, and here it is the alkali metals, and in the right hand side, it will be the alkaline earth metal. So whenever we are going from left to right in a periodic table, the effective nuclear charge actually increases. So whenever we are going from left to right, the effective nuclear charge increases. That's why the alkaline earth elements have effective nuclear charge more than that of the alkali metals. That's why the atomic or ionic radii are even smaller than those of the alkali metals. So alkali metals are actually bit larger in size, but the alkaline earth metals will be a bit smaller in size. So how you will remember this thing? So there is a gentle trick here. There is a gentle trick here that you can account for. In the left hand side, that is the alkali earth metals, they have smaller electron, they have the smaller isotopic value, or you can say their atomic numbers are less. So less atomic number, and they have less charge. So they have +1 charge. So alkali metals have less amount of charge. Alkali metals have less atomic number. So they will be larger in size. So it will be just the opposite. So if they are having less atomic number or less charge, so they will have more size or larger size. And these alkaline earth metals are actually lying right to the alkali metal. So they have more amount of charge because they are having +2 charge. They have more atomic number because they have one more electron here. And that's why their size will be smaller. So in this case, the entire thing by the which you will remember these things will be thus the opposite. So if the element is having less amount of charge, the atomic or ionic radii will be larger. And if the alkaline earth metal, so they are having some more atomic number or more amount of charge, then they will be smaller in size. So that's how we will remember the atomic or the ionic radii trend between the alkaline earth metal and the alkali metals. So in the next section, we will discuss about. So now you are having these alkali metals here. And here you are having these alkaline earth metals. Now these alkali metals are left in the periodic table. So you will find here what is the first element here? That is lithium. And in the right hand side, what is the first element you will find here? It is the beryllium. Now I have told you from left to right, if we go from left to right in a periodic table, then the effective nuclear charge will be increased. That's why the atomic or the ionic radii will become smaller. Now you are going to the ionization enthalpy, that is the IE1. Now we shall go to the IE1 now. Let me erase it. So now we will discuss about the ionization enthalpy, that is the IE value. Now IE values are what? IE values means whenever suppose an atom is here, and it is an atom. So I'll denote it by A. So it is an atom here. And whenever in the valence shell, there are actually many shells here. You can see there are many shells for a principal quantum number with respect to that. So whenever an electron is, suppose an electron is sitting right here, and it is the valence shell. And so whenever the amount of energy that will be required to pull off this electron from the valence shell, so it will be kicked out of the valence shell. So how much energy will be required to pull off this electron from the valence shell? That is the amount of ionization enthalpy. Now you see the ionization enthalpy of this, we will count for the outermost electrons. Now you see here, it is a NS2. It is having the electronic configuration of NS2. So there will be having 2 electrons in the valence shell. One will be here and another will be somewhat here. Now it will be IE1 and it will be IE2. Now it is the first amount of energy that is required to pull off this first electron, and it is the second amount of energy that is required to pull off this second electron from the valence shell of the element. Now you see here the IE1 will be higher because if we pull off this one electron will, if it is pulled out, then it will have the electronic configuration NS1. Okay. So from NS2, we will go to NS1 if we give the energy IE1. But in the second section, whenever we are going to the second ionization energy, so from NS1, we will go to noble gas. That is, so if we give the energy I1, then from NS2, we will have the electronic configuration NS1. But if we then put the IE2, that is the ionization enthalpy 2, the NS1 configuration will go to the noble gas configuration. And you all know that noble gas configuration is very, very stable in nature. That's why, because this system is so much stable in nature, the amount of energy required in the second step, this is step 1 and this is step 2. So in the second step, the IE2 value will be much less than that of the IE1 value. That's why it is written here that IE1 is higher, but IE2 is lower than that of the alkali metals. Okay. So next we will go to the next section, that is the hydration enthalpy. So about this, I have told you in the last class, whenever we will talk about hydration enthalpy, the main thing that we will keep in mind, that is the ionic potential. So ionic potential value is actually denoted by this letter, that is phi. It is called as phi. So in circle, when it will be cut away, it will be denoted as phi. So this phi value is nothing but it will be cationic charge by cationic radius. So it will be charge, either it will be plus or it will be minus, and it will be divided by this radius value, that is small r. So you see, ionic potential value is actually directly proportional to the charge of the system, and it is inversely proportional to the radius of the system. So here I will write these two equations. The phi, it is actually directly proportional to the charge of the system, whether it is plus or it is minus, and if it is also inversely proportional to the radius of the system. So it is inversely proportional to r, and it is directly proportional to the charge. So the more charge will result in more phi, and the less amount of radius will result in a more amount of phi. That is the ionic potential. Now, whenever the system is having a more amount of phi, so if the phi value is high, then the hydration enthalpy, that is, will be denoted by He, that is the hydration enthalpy. Ionization enthalpy is denoted by IE, and hydration enthalpy will be denoted by H dot E. So whenever the phi value is high, the hydration enthalpy will also be high. So the more hydration enthalpy will result in more amount of dissolution. Now you see, their hydration enthalpies are much larger compared to the alkali metals. Why? Because alkali metals, either the AM metals, are having charge value of how much? It is only +1. But the alkaline earth metal, that is actually we are discussing now, it is the alkaline earth metals. So they are having how much charge? They are having charge of +2. Now I have said here that is the more amount of charge will result in more amount of phi, and more amount of phi will result in more amount of hydration enthalpy. So alkaline earth metals have more charge. That's why their hydration enthalpies are more than that of the alkali metals. But here also you can see their radius, you can see here is the atomic or ionic radii are also smaller. So in case of the alkaline earth metal, the amount of radii or atomic or ionic radii are smaller. That's why they are also hydration enthalpies are also more. For these two reasons, alkaline metals have much higher phi value than this one. That's why the alkaline earth metals have a very much hydration enthalpy, much larger compared to the alkali metals. The order follows as beryllium is more and barium is the least, because barium is the having the highest atomic number. It has the highest atomic radii. So the R value of barium is the highest. That's why the hydration enthalpy here is the lowest, because it is actually inversely proportional to the radius. So more amount of radius will result in a less amount of hydration enthalpy. So that's how, with the help of phi or the ionic potential value, we can actually say which element or which cations are more soluble in nature, or which have more amount of hydration enthalpy. Next. So next section, you will have this color shown in the flame test. Now all the many of these alkaline earth elements will show some characteristic color in the flame test. So there is a flame, there is a Bunsen burner, will be a flame here. And in the flame, these elements is alkaline earth elements will be put. Now, whenever the alkaline earth elements will be put to the flame test, the outermost electrons, that is the NH2 electrons, will get excitation from this energy of the flame. Now, these alkaline earth metals of the elements will then the electron will be excited, taking the energy from the flame, and then when it will be coming back to the ground state, it will release some energy that will fall in the visible region of the light. And then the color will be shown to our eye. So there is an electron in the valence shell, that is the NH2 electrons here. So it will be excited to the next energy state. Now when it will fall back, it will come to the ground state, then it will release the energy and it will fall in our visible region of the light. So the visible region of the light, we are having this VIBGOR from V, I, B, G, Y, O, R. So this is the VIBGOR or the color spectrum of our visible light region. In the VLR region, we are having this V as the least amount of this wavelength, and R is having the more amount of wavelength. So V having the least and R having the most. Now, somewhere in between, this electron will push out the energy, and we will see the color of the system. Now you see the beryllium and magnesium values have some high ionization enthalpy because they are smaller in size. That's why their electrons are very much tightly bound to the valence shell. That's why more amount of energy is required to pull off the valence shell electron of the beryllium atom. You see here, because from beryllium and magnesium, if we have to pull off the electron from the valence shell, we need some more amount of energy. That's why in the flame test, beryllium and magnesium do not respond. So in the flame test, you can see beryllium and magnesium do not respond at all. They do not show any color because the energy of the flame is not sufficient enough to push out the valence shell electron from the beryllium or magnesium. But whenever the case is there for calcium or strontium or barium, their sizes are much larger. So pull off the valence shell electron of calcium or to barium, it is quite easy. So the flame's energy can do so. That's why these three elements show some different kind of colors. So calcium shows brick red color, strontium shows crimson color, and barium shows this apple green color. So for your information, you have to remember this thing because these questions come in exam quite frequently, like which elements show which kind of characteristic colors in the flame test. And in this slide, you have seen here that beryllium and magnesium do not respond in the same because their valence electrons are too much tightly bound because they are having some high ionization energy. The last section that we will be discussing will be this reducing nature of these elements. So you know, because these alkali metals are strongly reducing in nature. So like them also, these alkaline earth metals are also very much reducing in nature, but the reduction property will be much lower than that of the alkali metals. You see here, there is a large hydration enthalpy of the small beryllium ion. So beryllium here is the strongest among the elements. Here in the last section, I have told you lithium was the one which was having some highest reduction potential value. So how you remember that the first element of the period of the group will be the strongest reducing agent. So lithium was the first element in the alkali metal group. That's why it was having the high reduction potential value. So it was the strongest reducing agent. Here also barium is the first element. So beryllium is the first element. So here also beryllium will having the highest reduction potential value. So that's how we will remember, like the smallest element or the first element in the specific group will be acting as the highest reducing agent or the strongest reducing agent. So these are the two reasons why they are the strongest one. The first reason is the large hydration energy of the small beryllium to ion. So how we will get to that? Because I have told it is having the highest phi value. because the phi value is high because the charge density is so much in beryllium, because beryllium is very much small in size, and that's why the charge density or the effective charge density, or you can say the ionic potential, or you can say phi value of beryllium 2 ion is so much high in nature. That's why it is having the highest hydration enthalpy. And secondly, the high atomization enthalpy value of the metal. So these two actually are the main factors that contribute to the highest or strongest reducing agent of beryllium being. So beryllium is the strongest among the alkaline earth metals in terms of reducible property. So in the next slide, we will discuss two things. Firstly, we will discuss about the anomalous behavior of beryllium. And in the second section, we will discuss about the diagonal relationship between beryllium and aluminium. So firstly, you can see here, in case when it was the case of the alkali metals, lithium was showing some anomalous properties. So whenever it is the first element in the group, it will show some of the properties that will not be shown by the other elements in the same group. So here also, beryllium is the first element in this group 2. That's why it will also show some anomalous properties, which will not be shown by the other elements in the same group. Now, firstly, it is having some exceptionally small atomic or ionic radii, because I have already told you it is the first element of the periodic of the group. So it does not fit well with its heavier congeners in the same group. It is having some exceptionally small atomic or other ionic radii. The second one is having the high ionization enthalpy and the ionic potential values. So IE value is already denoted by IE, and the ionic potential is having the value phi. So this beryllium atom is having some high ionization enthalpy because it is exceptionally small in size, and very high energy is required to pull out the last valence electron. And secondly, it is having a high ionic potential value. I have already discussed about it in the last slide, because it is having such a small size and it is having a high charge density. Now, it forms compounds which are mostly covalent in nature and which are easily hydrolyzed. So how this ionic potential value and covalency are related? Let me show you as an example. Suppose this is the cation here, and this is the anion here. So you see the cation is having some more effective nuclear charge, and these electrons are actually loosely held in the anion. Now the cation, or the nucleus of the cation, will try to pull off these electrons, because nucleus are already attracted to the electrons, because nucleus is positively charged and electrons are loosely bound. So nucleus will try to distort the electron cloud. Nucleus will try to distort the electron cloud in a specific anion. So more will be the polarizability of the corresponding anion, the more the electron cloud of the anion will be distorted by the corresponding cation. So it depends solely upon the nature of the cation, whether it will be able to distort the electron cloud of the anion with the help of the polarizability. Now, since beryllium is actually having some high charge density value, it is the nucleus is so much powerful in nature, so it will distort the electron cloud of the anion to it. That's why the electron cloud will be then mixed to the cation. And you all know, whenever some mixing of the electrons will happen, there will be chance of this covalent character, because covalency is nothing but mixing of the electrons. So here, whenever the phi value or the ionic potential value will increase, the mixing of electrons between the cation and anion will be more. And then the covalent nature in the compound develops. That's why whenever a specific cation is having some high ionic potential value, it will show covalent compound. It will form covalent compounds more. Now the third option is here. The beryllium exhibits coordination number 4 only, because it does not have more than 4 orbitals in the valence shell. Because you know, beryllium is having the principal quantum number, and in this principal quantum number, their more orbitals are not actually able to accommodate. That's why the other members of the group, like magnesium or calcium or strontium, they are quite larger in size. That's why you can see they are having the coordination number 6 because they can make their use of the d orbitals. But beryllium does not possess any d orbital because beryllium has principal quantum number n, that is 2. And for n is equal to 2, d is non-existent. D actually orbital starts from principal quantum number 3. That's why beryllium does not or is not able to make use of the d orbitals. It cannot extend its octet, or it cannot form more than 4 coordination number. That's why the beryllium shows some anomalous properties in bonding too. And lastly, it is the oxides or the hydroxides of beryllium. Like you can see that's beryllium oxide, or you can see that's beryllium hydroxide. These oxides or the hydroxides of beryllium, unlike the other elements, are actually amphoteric in nature. When the other elements, that is you are having magnesium or calcium or strontium, are actually alkaline in nature. That's why they are called alkaline earth elements. But you can see quite ridiculously, beryllium does not show any kind of this alkaline property because its oxides or hydroxides are actually not alkaline at all. Are not alkaline. They are amphoteric in nature. In the next section, we will discuss about the diagonal relationship between beryllium and aluminium. So in the last session, I have told about about these things, like beryllium is having some diagonal relationship with aluminium. You see, lithium is lying right here, and here it is sodium. Now beryllium is here, and magnesium is here. So it is the group 1, this is the group 2. And in between, we are having these d orbitals or d elements. So we will not talk about these d elements. So in group 3 or group 13 in the modern periodic table, we are having boron here. And this is aluminium here. So in the last slide, I have told you, you can see lithium and magnesium are diagonal to one another. That's why they are having some similar properties between them. Here also you can see beryllium and magnesium are diagonal to one another, beryllium and aluminium. So beryllium and aluminium also have some common properties between them. So what are these? Firstly, you can see that is the beryllium 2 is having this ionic radius as 31 picometer, which is very small in size. That's why the ionic potential value, that is the phi value, is charge by radius value, will be comparable to that of the aluminium 3. Since they are member of group 3, they are having the oxidation state as 3. They are lying in the group 2, so they have oxidation state 2. And they are in the group 1, so they will have the oxidation state plus 1. So whichever group they are lying in, the oxidation state will be corresponding plus 1. The next topic will decide, like aluminium, beryllium is not also attacked by acids because of the formation of a thin oxide film on the metal surface. Suppose this is a beryllium element in the metallic form. So whenever it is exposed to air, it will react with the molecular dioxygen that is present in the air, and it will form this beryllium oxide. Now beryllium oxides are white crystalline substances. Now they will be covering the surface of the beryllium atmosphere too much. So the oxygen will not be able to react with the corresponding beryllium surface. So then it will not be hampered. So whenever beryllium is actually kept in acid or any kind of open air, then a thin oxide film will be, that is a beryllium oxide, will cover the metal surface. So the other agents like acids or bases or alkalis or other agents will not be able to tamper the beryllium metal surface. So then it will not be affected at all. Now here you can see this beryllium hydroxide dissolves readily in excess alkali to produce this berylate anion, BeOH whole 4 2 minus. And like AlOH whole 3 similarly produces aluminate anion, that is AlOH whole 4 minus. So in this case also beryllium and aluminium show some similar properties. Now both of the chlorides, like beryllium chloride or you can say aluminium chloride, they form bridging structures in vapor phase. They are also soluble in organic solvents. They are strong Lewis acids and they are used in the Friedel-Crafts analysis. So here beryllium chloride or aluminium chloride, all these are used in Friedel-Crafts analysis. They are having some significantly strong Lewis acidic behavior also, and they also have this they are soluble in organic solvents. So Lewis acids mean nothing but they can attract the electrons. Since beryllium or aluminium both are having some high charge density, the phi value is quite high, so they will attract the electrons. That's why they are called as Lewis acid. And lastly, what is the main similarity between these two? Both of these actually elements react with fluoride anion. They have strong tendency to react with fluoride anion, that is the F minus anion, and they will form these similar kind of compounds. Firstly, this is BeF42 minus, and aluminium also forms AlF63 minus. Both of these compounds are white crystalline solids. Now, with all these things in our arsenal, we will go to the question answer session. The first question will be beryllium and magnesium do not give rise to colored flames, but the other alkaline earth metals do so. Why? So I have already discussed about in the first slide, like beryllium and magnesium possess ionization enthalpy values around 900 and 740 kilojoule per mole. So you can see that what are the values here? The values are actually so much high in nature. So their ionization enthalpy values are quite high. So the energy that we will have from the flame will not be sufficient enough to excite the electron to the ground, from the ground state to the excited state. This is the ground state of the electron, and this is the excited state of the electron, ES. Now, if we put the energy to the electrons, they will actually get pulled out from the valence shell and they will jump from the ground state to the excited state. And when they will come back, their energy that will be released will be seen by us in the form of a color. So in the form of a color, we will see the electrons will come down to the ground state on the excited state. Now, if you can see that the beryllium and magnesium, both of these compounds possess such high ionization enthalpy value. First one is the 900 kilojoule per mole, and magnesium possesses 740 kilojoule per mole. So this amount of energy is not actually produced by the flame. That's why the valence electrons are too much tightly bound in case of beryllium and magnesium. So from the outermost shell, it will not get released at all. That's why they do not impart any kind of characteristic color in the flame test. But the other elements like calcium or strontium or barium, they are larger in size, so their ionization enthalpy values will be less. So in those cases, the electrons will easily get expelled out from the outermost shell. That's why they will show some significant color in the flame test. So in the next question, we will discuss about the solubility and the thermal stability of the following compounds of the alkaline earth metals. First one is the nitrates, the second one is the carbonate, and the last one is the sulfate. Now, in these cases, we will have to discuss about two things. First one is the solubility, which is quite prevalent here, and the second one is the thermal stability. The first one is the water solubility. Solubility here will account for the water solubility already. Now, whenever we will discuss about the solubility in water, firstly, we will start with the hydration enthalpy. Like I have already suggested you this thing. Whenever water solubility will come into picture, we will discuss about the hydration enthalpy, that is H.E. Now, whenever hydration enthalpy will be coming into picture, it will be directly related to the ionic potential value. So it will be related to this phi value. Now, the phi value is actually directly proportional to charge and inversely proportional to the radius. That's why less amount of radius will result in high amount of ionic potential value, and high amount of ionic potential value will result in a high amount of hydration enthalpy. So if the atom is having less radius, it will be more soluble in water. So in case of beryllium, the compounds will be highly water soluble. So whenever we will come into picture, when beryllium two compounds will come into picture, you will find they will be highly soluble in water because their hydration enthalpy is so much high because of the very less amount of radius and high amount of charge. So how you will remember this thing? The radius, if it is low, the solubility will be high. That's how you can remember this is one of the basic tricks here. Like for whenever we discuss about the water solubility, when the radius will be less, the solubility will be more. So beryllium 2 compounds will be highly soluble in water. Those are opposite will happen for barium. Barium is having the highest amount of radius, so it is having the lowest amount of phi value. The phi value of barium compounds are lowest. That's why they are not soluble in water actually. So whenever will this come into picture, these nitrates or carbonates or sulfates, so this is the factor of the water solubility. Now we will come to the factor of the thermal stability. So how they react when they are put to thermal energy. Now here the first thing that will come into picture, that is the comparison of size between the cation and the anion. So the cation is here at the alkaline earth metals, and the anions will be different. So the anions will be sulfate or carbonate or nitrate or phosphate, or the anions can be oxide or hydroxide or fluoride or chloride. So anions can differ also. But in this case, the cations are fixed from beryllium to calcium. Let me actually erase this part to show you in a better way. So you see here, first we are starting with beryllium and last we are having this barium. And the size is actually increasing from beryllium to barium. And in the left hand side, we will have the anions. So we will have a set of large anion and we will have a set of small anions. So we are having this large anion as sulfate, or we are having this large anion as carbonate. Or in this second section, we have this cation as anion as F minus, or we are having this oxide or this hydroxide. So they are actually small anions and they are actually large anions. Now you can see here the sulfate, carbonate or nitrates all are large anions, but fluoride, oxide, OH minus, we are small anions. Here the beryllium cations are actually smaller in size, but whenever we are going from beryllium to barium, the size actually increases. So the size matching will be with barium to sulfate or carbonate or nitrate, and here the size matching will be from beryllium will be with fluoride or oxide or hydroxide. Now, whenever you will see small cations, they will prefer small anions. So small cations will prefer small anions and large cations will prefer large anions in nature. Now, whenever thermal actually stability is coming into picture, you will find this barium sulfate is thermally most stable because large cations will actually be in love with the large anions. So they will be more stable. So thermally that will not degrade. But I have already told these beryllium compounds are actually is having some good connection with the small anions, because in that case, you can put up the argument like that, like small cations and small anions will have the comparable ionic radii. So they will fit more in the unit cell. And large cations will also fit with large anions. They will also fit in the unit cell. So beryllium compounds will not have a very stable bond or stable amount or stable compound with the sulfate or the carbonate or the nitrate. But barium compounds will have, or the strontium compounds will prefer the large cations like sulfate or carbonate or nitrate or phosphate. These beryllium compounds will have or have preference with the smaller anions like fluoride or chloride or oxide or hydroxide. So whenever we are going from top to down the group, the thermal stability actually increases because beryllium compounds will prefer the larger anions like sulfate or carbonate or nitrate or phosphate. But this beryllium will, and this whenever this carbonate or the sulfate will be actually thermally heated, they will produce the corresponding oxide values. And these oxides are much stabilized by the smaller cations. So whenever beryllium carbonate is heated, it will readily form beryllium oxide because beryllium oxide is very much is having a high lattice enthalpy because beryllium and oxides are actually having similar size. Both are small. The beryllium cation is small and the oxide anion is also small. So that will readily form these oxides. So their thermal stability is very much less. but the corresponding barium compound is highly stable in thermal conditions. The next slide we will discuss about the standard electrode potential. In the next slide we will discuss about the standard electrode potential value for the M2 plus aqueous, two electrons, that is M solid, or M is calcium or strontium or barium, are nearly constant. So you might have encountered in the periodic table, like these E0 values will depend solely on the different parameters. What are the parameters? So the parameters we will have to remember in this way. So here are the parameters, like the enthalpy of vaporization. The second one is the ionization enthalpy, and the enthalpy. So these three are actually very much important factors to account for the standard electrode potential of any electrode. So here it is the M2 plus to M electrode. M2 plus to M electrode, where M are calcium, strontium, and barium. Now, first one is the enthalpy of vaporization that you have to remember. Second one is the ionization enthalpy. And the third one is the hydration enthalpy. So these three factors you have to remember. Now, how we will account for these factors? Firstly, you can see that these are the three factors that will combine and that will give rise to the standard electrode potential value, that is ACP. Now, this ACP value depends on the summation value of these three factors. First one is the enthalpy of vaporization. Second one is the ionization enthalpy. And the third one is the hydration enthalpy. So we are having factor 1, factor 2, and factor 3. Now, all these factors are actually not having any kind of similarities or correlation between one another. Now, how we will account for this? Factor 1, factor 2, and factor 3 are coming into picture, and their combining effect is actually reflected in the standard electrode potential. The standard electrode potential will then govern how they are more reducing or less reducing in nature. Now, experimentally, whenever these experiments were carried out in the laboratories, it has been found that the three aspects, aspect 1, these 2, and 3 are having some combining effect of nearly the same for these three metals. Like calcium, in case of calcium, the total value of these three factors is some X value. For strontium, the total factor will be X value. And for barium also, it has been obtained that the combining effect of the three actually factors will be same. So in all the cases, whenever it is calcium or it is strontium or it is barium, the combining effect of all the three factors are nearly the same, more or less the same. So how we will account for it, or how we will see this thing through the naked eye? Now you can suppose you today a person A is having 3 apples, and yesterday he got 2 apples. So total he got 5 apples. Now B, the person ate today 2 apples, and yesterday he ate 4 apples. So total it ate 6 apples. Now the C person is eating 3 apples today, and yesterday it also ate 3 apples. So total 6 apples. So the ratio, if we are going to like A, B, C, will be 5:6:6. So the ratio will be 0.8:1:1. So you see the total factor is actually remaining the same, because total factor is actually governing by the summation of the three factors. So whether it will be 3 plus 2 or 2 plus 4 or 3 plus 3, all in the cases they will result in the more or less same value. That's why in case of calcium, this enthalpy of evaporation is less, but the ionization enthalpy will be high. But in case of strontium, the enthalpy of evaporation will be less, but the ionization enthalpy will be high. You can say in case of barium, the hydration enthalpy will be less, but the enthalpy of evaporation will be high. So the combining effect of all the three parameters for these three metals will be more or less same in this case. That's why whenever we are combining these three factors, they are generating similar electrode potential value. That's why if you see, their electrode potential values are very much close to one another, like in the range -2.1 or -2.2. So they are approximately the same. In this case, we will discuss some basic small questions which are actually very much important for the exam purpose. So first question is whenever powdered beryllium burns in air, it produces what? First option is beryllium sulfate. Second option is beryllium oxide. Third option is beryllium nitride, Be3N2. And the last option is both B and C. So among all the alkaline earth metals, whenever beryllium is actually heated in air, so beryllium will be the only metal that will react both with the oxygen and nitrogen, because these are actually present in the air. Amount of oxygen is 21, amount of nitrogen is 78%. And the rest amount will be governed by the moisture or the inert gases, etc., etc. Now, N2 is found in the more, so beryllium will readily react with molecular dinitrogen to produce this Be3N2. And since we are having 21% oxygen, beryllium will also react with oxygen to produce beryllium oxide. So both BeO and Be3N2 will be formed. So the correct option is option B and C. Both B and C will be formed. The next question is, can beryllium hydride be prepared by combining beryllium solid with H2 through heating? The options are yes, no, maybe, may not be. The correct option is no. Beryllium cannot be coupled with molecular dihydrogen to produce BeH2. So in that case, an alternative pathway is actually depicted here. So beryllium chloride will be reduced by lithium aluminium hydride. This lithium aluminium hydride is a very strong reducing agent. Lithium aluminium hydride is a very strong reducing agent. So this LiAlH4 will react with the BeCl2 to produce this BeH2. Actually, it will transfer its hydrogen to the corresponding beryllium center, and the aluminium atom will grab the chloride. So the byproducts will be AlCl3, because you know AlCl3 is very much stable, and the other byproduct will be lithium chloride. You know lithium has a very high affinity towards chloride because it is an S block element, and S block elements are actually fond of the halides. So lithium chloride is one of the byproducts, AlCl3 is the other byproduct, and will form this beryllium hydride. The next section, the question will be which one among the following is a component of the milk of magnesia. So you might have encountered about this antacids. So antacids are whenever we are eating something, we generally suffer from this acidity problem. You might have encountered whenever we are drinking milk, and then if we have some chicken tikka or such kind of thing, we will suffer from this acidity. And whenever we are suffering from acidity, we go to the medical shop. We actually ask for this kind of Gelusil or kind of Rantac, such kind of things. So what are those? So acidity means we are developing extra amount of acid in our pancreas, so or liver. So we have to neutralize the amount of acid. So in our belly, we are having acid. So it is a problem with acidity. Now to counter this acid, we need to add a base, because you know acid and base will react with one another to produce a salt, which is actually readily soluble in our environment or our biological fluid. The salt will be soluble in our biological fluid. That's why whenever suffering from acidity, we search for a base. So these are actually called the antacids, because they are actually anti of the acids. In medical term, they are called as the antacids. Now, what are these antacids? The popular antacids, all of you know about the Gelusil. We have Gelusil when you are suffering from antacids. The milk of magnesia is also one of the major antacids. It is nothing but magnesium hydroxide. Whenever magnesium hydroxide is put in water, it forms a suspension. It does not actually dissolve in water. So this actually, and magnesium hydroxide is actually white in nature, white crystalline powder. So whenever magnesium hydroxide is actually put in water, they form a milk kind of thing. It actually resembles kind of milk. That's why it is called milk of magnesia. Magnesia comes from magnesium, and since it resembles the structure or the value of the milk, that's why it is called the milk of magnesia. So it is one of the major antacids here, so which you actually we drink, because whenever we are suffering from this acidity problem. So the correct option is not MgO, not magnesium sulfate, not MgCl2, but MgOH whole 2 is milk of magnesia. Now, which are the alkaline earth metals that have significant biological importance? The first one is the magnesium. Magnesium, we have all known about that. It is an important cofactor for the enzymes that use ATP in the phosphate transfer. So in plants, magnesium is actually having one of the major importances. It is one of the major cofactors. And you all know about chlorophylls. Chlorophyll is one of the major pigments for light absorption by plants. You have known that the color of the plants, the beautiful green color of the leaves, that are actually responsible because they are chlorophyll. Chlorophyll is responsible for the color, and chlorophyll contains this magnesium. And the calcium. Calcium is also having some vital roles. You might have known about this major component about bone and teeth. So whenever we are suffering from less calcium deficiency, our bones will be weaker, our teeth will not be able, we will not be able to bite or eat some strong kind of food like guava kind of things. So the major component of bones and teeth are calcium. Calcium also have some other properties or other roles. First one is the neuromuscular function, interneuronal transmission, cell membrane integrity, and blood coagulation. So in all these cases, calcium is having some vital roles. The major role is actually having the increasing the density of the bones and the teeth. So in the next question, we will discuss about which one of the alkaline earth metal hydroxide shows amphoteric behavior. So I have already discussed about it. Which one is showing the amphoteric behavior. So in the alkaline earth metals, you must have wondered why it is the question. Because when I am saying the metal hydroxides are alkaline, why it is showing some amphoteric behavior? That is the problem with the beryllium. Beryllium is the only alkaline earth metal that is actually, that hydroxide does not show any alkaline property, but rather it shows amphoteric behavior. So what do this amphoteric term means? Amphibian, you might have encountered the animal kingdom, the animals that can actually stay in water and also stay in the land, they are called the amphibians. So whenever both of the things are actually okay with the system, they are called the amphoteric property. So in both the cases, they will react. So since beryllium hydroxide reacts both with acid and alkali, so that's why it is amphoteric in nature. So beryllium hydroxide is not an alkaline earth metal hydroxides. These are the two cases. I have actually picked the example. With alkali, you see, whenever beryllium hydroxide is treated with an alkali, it will produce this beryllium berylate anion, BeOH whole 4 2 minus. So it reacts with alkali, and surprisingly, it reacts with acid also. So beryllium hydroxide, when it is reacting with the Bronsted acid HCl in aqueous medium, it will form this complex BeOH whole 4 2 plus Cl 2 minus. So it forms both BeOH whole 4 2 plus, and it will form this BeOH whole 4 2 minus. So this is the showing of the amphoteric property of the beryllium system. The last question that we will discuss here will be explanation why MgCl2 or CaCl2 readily forms hydrates, but sodium chloride or potassium chloride don't. NaCl and KCl are the alkali metal salts, but this MgCl2 and CaCl2 are the alkaline earth metals. Now, whenever we are discussing about the formation of hydrates, we will discuss enthalpy of hydration that I have told you, and it will be governed by the ionic potential value that I have giving very much importance in this chapter. Ionic potential value, that is phi. Now the phi value is actually directly proportional to the charge, and it is inversely proportional to the radius. Now you know I have already told, like the magnesium or the calcium, these elements are having less amount of radius and they are having high amount of charge, +2 charge. That's why the phi value of magnesium or calcium will be higher than the phi value of sodium or potassium. So when the phi value of magnesium or calcium is higher than the phi value of sodium or potassium, the ionic potential value or the enthalpy of hydration will be more in case of magnesium or the calcium salts. But it will not be good for NaCl or KCl. That's why MgCl2 or KCl2, whenever we are keeping this in the air or in the moisture, they readily catch H2O and they form these kind of hydrated salts. MgCl2.6H2O, 6CaCl2.6H2O. But whenever you see NaCl or KCl, you might have not encountered about NaCl dot some H2O or KCl dot H2O because they do not catch up water because their ionic potential value is quite low. But magnesium or calcium, because they are having a high charge or less amount of radius, that's why they are having more ionic potential value. So they have more amount of tendency to form the hydrates. That's why these salts are actually found in nature at the corresponding hydrates. But the alkali metals do not form this kind of hydrates. So with this, I will draw the conclusion to the S block elements session 2. So our S block elements chapter is now over.